Let's explore linear motion when acceleration is constant, focusing on the SUVAT equations. These equations are essential for solving problems involving objects moving in a straight line with uniform acceleration. Throughout this presentation, we'll break down what each variable represents and how to use the equations effectively in physics. Let's get started. To use SUVAT effectively, the motion must be in a straight line, ensuring we can analyze the displacement and velocity clearly without changing directions. The acceleration should remain constant throughout the motion, meaning it doesn't speed up or slow down unevenly. It's also important that no external forces change during the interval, so the motion stays predictable. Finally, measurements or observations need to be taken at uniform time intervals to keep the data consistent for analysis. Meeting these conditions helps us apply the SUVAT equations accurately and understand the motion precisely. Now, let's define the key quantities we use in SUVAT equations. Displacement, represented by S, is the distance moved in a specific direction, measured in meters. The initial velocity, u, is the speed at which an object starts moving, measured in meters per second. Final velocity, v, is the speed the object reaches after acceleration, also in meters per second. Acceleration, a, is how quickly the velocity changes, measured in meters per second squared. Lastly, time, t, is the duration over which the movement occurs, measured in seconds. These 5 quantities help us describe motion in a clear, consistent way. Now, let's focus on the concept of constant acceleration. This means that acceleration remains the same throughout the motion, without any variation. Because acceleration is constant, velocity changes at a steady, linear rate over time. Meanwhile, the position or displacement of the object changes in a quadratic pattern, increasing more rapidly as time progresses. This relationship allows the graphs of acceleration, velocity, and position to follow predictable and well-defined shapes, making it easier to analyze and understand the motion involved. This equation shows that the final velocity is equal to the initial velocity plus the increase in velocity caused by acceleration over a period of time. It directly connects how an object's velocity changes over time when it is subjected to constant acceleration. This formula is particularly useful when we want to find velocity without needing to know the displacement. It also describes a simple linear change, meaning that velocity increases or decreases at a steady rate. This relationship helps us understand motion in a straightforward way, especially in cases where time and acceleration are the main factors affecting velocity. This equation connects displacement with time by considering initial velocity and acceleration. It shows that displacement depends on both the time elapsed and the square of the time, which means the relationship is quadratic. This equation is especially useful when you don't know the final velocity but need to find out how far an object has traveled based on its starting speed and acceleration over a certain time period. Let's move on to the third SUVAT equation, which is written as v squared equals u squared plus 2as. This formula is useful when you don't have the time variable in your problem. It comes from the previous equations and helps you calculate the final velocity squared based on the initial velocity squared, the acceleration, and the displacement. This way, you can solve certain motion problems without needing to know the exact time involved, making it especially handy in situations where time isn't given. This equation shows how displacement can be calculated using the average of the initial and final velocities multiplied by time. It only works when acceleration remains constant, which means the velocity changes at a steady rate. By using this formula, we can directly connect the distance traveled to the duration of the motion, keeping it simple and effective for those conditions. When trying to choose the right equation to solve a problem, it's important to follow a clear process. First, identify all the variables you already know, like distance, time, or initial velocity. Next, figure out which variable you need to find. That's your unknown. Then, pick an equation that includes all the known variables and the unknown, but doesn't involve any variables you don't have information about. Finally, always check the units in the equation to make sure everything aligns correctly. This approach helps avoid confusion and ensures you use the right formula for the situation. Next, let's take a closer look at the velocity time graph. When acceleration is constant, the graph appears as a straight line. The slope of this line, or the gradient, represents the acceleration. If you calculate this gradient, you get the rate of change of velocity over time, which is acceleration. Additionally, the area under this line corresponds to the displacement of the object during the time interval shown. The point where the line crosses the velocity axis indicates the initial velocity before any acceleration occurred. Understanding these components makes it easier to analyze motion using the graph. This graph shows how displacement changes over time, represented by a curve that forms a parabola. The key point here is the gradient of the curve at any given point, which represents the velocity at that moment. Because the curve is curved rather than straight, it tells us the velocity is not constant. The curvature indicates acceleration is happening. When the slope of the curve becomes steeper, it means the velocity is increasing. So, by looking at the steepness and shape of this graph, we can understand how the object's speed changes as time progresses. Now, let's look at the acceleration time graph. When acceleration is constant, it's represented by a horizontal line on this graph. The area under this line corresponds to the change in velocity over that time period. This means if acceleration is positive, velocity increases. If negative, velocity decreases. When the acceleration is zero, it indicates the velocity remains constant because there is no change occurring. This graph helps us visualize how velocity changes as acceleration varies over time. When we talk about freefall, we're looking at a special case of motion where acceleration is caused only by gravity. This acceleration is constant and has a value of 9.81 meters per second squared. Depending on how you set up your coordinate system, downward direction can be considered positive or negative, but either way, the same equations of motion still apply. Essentially, free fall simplifies the problem since only gravity acts on the object, making calculations more straightforward while using familiar formulas. Next, let's focus on some key points to keep in mind for the IB exam. It's important to clearly state any assumptions you make during your calculations or explanations. When you're using equations, be sure to show your substitution step so that the examiners can follow your thinking. Always include the correct units in your final answers. They matter a lot in demonstrating your understanding. Lastly, make sure you use the correct sign conventions throughout your work, as this helps avoid confusion and ensures accuracy. Keeping these in mind will help you present your solutions clearly and confidently. Let's take a moment to review some common mistakes that often come up. One is using SUV8 equations when acceleration isn't constant. That can lead to incorrect results because those equations assume uniform acceleration. Another frequent error is mixing up velocity with speed. Velocity includes direction, while speed does not, so confusing the two can change the outcome. Sign errors are also something to watch out for, especially when dealing with directions and vector quantities. Lastly, forgetting the squared term in equations, particularly when it's part of the formula, can throw off your calculations. Paying attention to these points will help avoid errors and improve accuracy. To wrap up, remember that the concepts we've discussed apply only when acceleration is constant. The system involves 5 key variables connected through 4 fundamental equations, and using graphs alongside these equations helps make their relationships clearer. It's also important to always define your sign convention before solving any problems so your calculations stay consistent and accurate. This summary highlights the key points to keep in mind as you apply these principles moving forward.